Introduction: Microchips unveiling the future. In the rapidly evolving landscape of technological advancement, microchips have emerged as the unsung heroes orchestrating a symphony of transformation. From their humble beginnings to the intricate marvels of today, microchips are propelling us toward a future defined by unprecedented innovation, connectivity, and integration. This exploration embarks on a journey through the history, significance, and promising trajectories of microchips, unraveling their role as the cornerstone of our technological destiny. In the ever-accelerating journey of technological progress, microchips stand as the unassuming architects of a digital revolution that is reshaping the fabric of our world. From their inception to the intricately woven circuits of today,
microchips are scripting a narrative of boundless possibilities, fusing innovation, connectivity, and integration. This exploration embarks on an odyssey through the historical lineage, profound significance, and tantalizing trajectories of microchips, unraveling their role as the pivotal linchpins of our technological odyssey. The basic framework, laying the groundwork as the world transitioned into the 21st century, the foundational groundwork for the microchip era was well underway. These minute yet prodigious components, constructed through intricate layers of etched silicon, were already powering rudimentary calculators, appliances, and personal computers. The pivot from bulky vacuum tubes to transistor-based microchips marked a seismic shift, introducing enhanced efficiency and intermediate evolution, pioneering progress in the unfolding years. Microchips evolved from being mere agents of computation to the architects of a digitized cosmos. The convergence of enhanced processing power and miniaturization catalyzed a paradigm shift that impacted every facet of contemporary existence. The smartphone, a quintessential marvel of microchip wizardry, democratized access to information, transformed communication, and revolutionized entertainment. Nurtured within these handheld marvels was the burgeoning seed of artificial intelligence, nurturing personal assistants and predictive algorithms that elevated convenience and efficacy. The mid-2000s bore witness to the advent of the Internet of Things (IoT), an epoch in which microchips ingeniously knit together devices, from home appliances to industrial machinery, into a sentient network. This fusion of connectivity and sensory acumen laid the bedrock for smart cities, precision agriculture, and healthcare innovations, ushering in an era where industries are reshaped and data-driven insights assume unprecedented significance. Advanced Horizons, envisioning the unthinkable as the chronicle of time unfurls, microchips are poised to traverse uncharted frontiers. Quantum computing, a realm where the marvels of quantum mechanics amplify computational might, promises to crack the enigma of previously insurmountable challenges. The once esoteric notion of neural interfacing gains traction, forging a path toward symbiotic relationships between microchips and the human brain, heralding revolutions in medical treatments and human augmentation. This surge of progress births ethical and existential quandaries. The convergence of microchips, artificial intelligence, and biotechnology beckons contemplation on the boundaries of consciousness, privacy, and individuality. As microchips transform from passive tools to active co-creators of reality, societies grapple with choices that shall sculpt the visage of a profoundly altered future. Conclusion: a harmonious symphony of progress. From their nascent beginnings to their contemporary ubiquity, microchips epitomize an extraordinary journey, crystallizing into the bedrock of our technological edifice. The year 2000 acted as a nexus, thrusting microchips beyond the realm of mere computation into an era of seamless interconnection, sentient ecosystems, and the precipice of quantum supremacy. Amidst the undulating currents of the future, microchips persist at the vanguard, poised to unveil the cosmic enigmas, stretch the boundaries of human capacity, and redefine the essence of existence. The saga of microchips is an ode to the unyielding human spirit to innovate, adapt, and wholeheartedly embrace the uncharted horizon. We are at the bottom of the product entity structure. There is nothing subordinate to this level. The parts are commonly electronic chips, switches, and wiring, but may also include plumbing valves and mechanical devices. Commonly, these will be purchased parts that have been developed and qualified by suppliers and identified by design engineers on engineering drawings that will have to be purchased from suppliers with a good reputation by procurement. Materials will take the form of sheet steel or aluminum, bar stock, or tube stock, for example, that are listed on engineering drawings and purchased from suppliers. Processes will commonly be prepared by the enterprise to control manufacturing processes, such as etching a metallic surface as a prerequisite to applying some kind of protective coating. These process standards will be listed on engineering drawings and in manufacturing plans and procedures. Microscopic atom optics, from wires to an atom chip. Ron Folman, Karsten Henkel, in Advances in Atomic, Molecular, and Optical Physics, 2002. A.2 nanofabrication atom chip structures can also be fabricated into an evaporated conductive layer with state-of-the-art processes used for electronic chips. To the best of our knowledge, this approach is only used by the Heidelberg, formerly Innsbruck Group. In these atom chips, a 1,5M gold layer is evaporated onto a 0.6 mm thick semiconductor substrate GaAs or C. As GaAs or C tend to leak currents, especially in the presence of light, a thin isolating layer of SiO2 is put between the substrate and the gold layer. The chip wires are defined by two 10M wide grooves from which the conductive gold has been removed. This leaves the chip as a gold mirror that can be used to reflect MOT laser beams. The 10M grooves impede the MOT operation only in a very slight way. The mirror surface quality is very high, achieving an extremely low amount of scattered light. The chips were produced at the microfabrication centers of the Technische Universität Wien and of the Weizmann Institute of Science, Rehovot. Electronic Supply Chain Svaru Bunia, Mark Tiranopour, in Hardware Security, 2019. 6.6.7 ECID and PUF-based authentication. ECID and PUF-based authentication approaches have been proposed to identify remarked and cloned ICs. The main idea here is to tag ICs with unique IDs, and track them throughout the supply chain. The electronic chip ID-based ECID-based approaches rely on writing the unique ID into a non-programmable memory, such as one-time programmable, OTP, and ROM. This requires post-fabrication external programming, such as laser fuses, 80, or electrical fuses eFuses, 81. The eFuse is gaining popularity over the laser fuse because of its small area and scalability, 81. Alongside ECID, silicon physically unclonable functions PUFs have received much attention as a new approach for IC identification and authentication, 82, 83. Silicon PUFs exploit inherent physical variations, process variations that exist in modern integrated circuits. These variations are uncontrollable and unpredictable, making PUF suitable for IC identification and authentication, 2884. The variations can help generate a unique signature for each IC in a challenge response form, which allows later identification of genuine ICs. In particular, this characteristic is met by neural and reconfigurable computing structures. Field programmable gate arrays FPGAs in which each unit cell is enhanced by an optical input and output node, 126, have been chosen as a vehicle for an OCI system demonstrator in the European Commission-funded Optically Interconnected Integrated Circuits OIIC project.